Okay. So we're beginning, I think, section 3.2. We're going to learn what we call conditional probability. And I'm going to explain, just this concept through an example. I'd like you to look at this table, first of all. The table shows the results of a study in which researchers examined a child's IQ in the presence of a specific gene in the child. So I want to see if there is a relationship between the IQ and the presence of a special gene. So you have this table, and this table is called contingency table, and I'm going to explain it to you guys because you need to know how to read the table. For example, guys, if I ask you what does the number 52 mean right here, how would you explain that? What is 52? 52 is the result of adding 33 and 19. What does it mean? Would anyone can tell
The
me?
number of people who have the high IQ.
Exactly. It's the number of children who have high IQ. 50, guys, means the number of children who have normal IQ. Now let's go this way, this total, vertically. The 72, guys, means the number of children who have the gene present in them. The number 30 is the number of children uh, who has the gene not present, so don't have the gene in them. Okay, would someone can tell me what 102 represents? 102, that's an important number that we're going to need today.
The total of high IQ and normal IQ
So
together.
the total of all children, everybody is included in this one, exactly. Okay, can someone tell me what 39 means here? You need to understand the table in order to be for me to answer the question.
39 children has that gene, the normal IQ.
Just the normal IQ,
That gene present.
the gene present, and the normal IQ, exactly. What about number 11? What does it mean? There are 11 children who have the normal IQ and don't have the gene present. So when you have a number inside the table, not the rows total or column total, guys, so the 39 stands for normal IQ and gene present. The 33 stands for children who have high IQ and at the same time has the gene present. 19 represents the number of children who have high IQ and at the same time the gene is not present. So if you guys understand what I explained, just about reading the table, I think we're ready to start answering some questions. I'm going to begin with part B. I think we can answer part B. Watch. We select a child at random. We're selecting a child at random. You just pick one child. What is the chance? What is the probability that selecting a child with normal IQ? As I told you, the definition of probability is the number of favorable outcomes divided by number of possible outcomes. Okay, we're selecting a child at random, guys, from the entire group. So what do you think the denominator is?
102.
Exactly. We don't know what is going to come up, so we're getting it from the group of 102. Now, the numerator is what would work in the favor of the question. And the question is telling you, I wanted to select someone with a normal IQ. So how many children are there who have a normal IQ?
50.
50. I did this question last semester and a student told me 39. But I told the students, I don't care whether the gene present or not present. We want only normal IQ. It doesn't put restriction on the gene. So normal IQ, it's not 39, it's not 11, it's the total here, which is 50. And that's the answer, guys, 50 over 102. If you were doing this in my lab and he asked you round the answer to 3 decimal places, just divide 50 by 102, and you will get 0.490, for example. That's 3 decimal places. All right. Okay, I'm gonna do one more question, guys, before I go to A and C here. Find the probability that a child selected at random. It's always at random. We're not looking how we're selecting. Has gene present. What's the probability of selecting a child at random who has a gene present? So you guys agree with me that the denominator here, it's 102. That's the big number. These are the possible outcomes. How many children are there who have the gene present?
72.
Yep. And that's the answer. It's 72 divided by 102, which is 0.706 if you round it to 3 decimal places. All right. So this is something we learned already, guys. This is the classical definition of probability. This is what I'm doing. I'm just using the definition of probability. Let me ask you a verbal question here, guys. What's the probability of selecting a child who has the gene present and has a high IQ at the same time? So who have the gene present and with the high IQ? What would be the answer? Give me the ratio.
33 over 102.
33 over 102. Because there are 33 children, guys, who have the gene present and with the high IQ out of the big number, which is 102. All right. Let's go to A. That's in some new stuff. Let's see if some of you can help me answer this one. What is the probability of selecting a child who has a high IQ given? Let me explain what given means. That's a condition he's putting on us. Given that the child has the gene. So we know already that the child has a gene. He's only asking us to select from the pool of children who have the gene. When I put a given condition, that means that's a must. It has to happen. So what would be the probability of selecting a child with a high IQ given that the children has the gene already? What do you think, guys?
33 over 72.
And that is correct, and let me tell you why. When he says, given that the child has the gene, he's telling us you only can select from the group of children who have the gene, not from anyone, the 102. The 102 is no longer valid anymore once you see the given statement. So what comes after given is going to be our denominator. So the child has a gene, and look, the total of children who have the gene, guys, is 72. So you put 72. Now, what goes in the numerator, what would work in our favor? In our favor, we want a child who has a high IQ and already has the gene. Well, the number of children who have high IQ and already have the gene present, guys, is 33. So that would be 33 over 72. And if you use your calculator, 33 divided by 72, it will be 0.458. Any questions? I'm going to go to part C now. Find the probability that the child has the gene given that the child has high IQ. Okay, guys, here's the trick. Let me show you how to answer this question. Whatever comes after given goes to the denominator. So he's putting a condition on us. He tells us you only can select from the group of children who have a high IQ. How many children total, guys, have a high IQ? You can see it's 52. So that's a 52 goes here. Now, we want a child who has the gene and has a high IQ at the same time, because he forced us to select from the group of children who have high IQ. So how many children are there that have the gene and a high IQ at the same time? High IQ and the gene, where the two meet, guys? At 33 again. There will be 33 divided by 52. And if I divide that, I get 0.635 if you round to 3 decimal places. Any questions, guys, about this? I'm going to add one more, see if you can respond to it. So I'm going to add the part DE right here. I want probability that a child has normal IQ given gene not present. So what's the probability of selecting a child who has a normal IQ given that the gene not present? So he's telling me that you only can select from the group of children who don't have the gene. How many do we have total, guys, with children who don't have the gene? You can put it in the chat.
11.
No, we need the ones who don't have the gene, total, not normal or high Q, it doesn't matter, just total.
30.
Very. Look, gene not present, guys, it's a total of 30. Now, for this, guys, you need what works in your favor, a child who has normal IQ and the gene not present. So look what you do. You just draw a line, normal IQ here, and gene not present there, and where the two meet will be your number, which is 11, the intersection. And this is 11 over 30. That's how, this is what we call, it will be not 19, 11, because we want a normal IQ, not high IQ. He says normal IQ and the gene not present, so will be the 11. So it's 11 over 30. And this is what we call, guys, the conditional probability. And this is how you compute conditional probability. In the book, he defines conditional probability of two events like this. And let me tell you what that means. The vertical line means given. So what's the probability of one event happens given that the second event happens at the same time? For example, if I look A, guys, look at A. Which one is A? Which one is B? What is the probability that the child has high IQ? This is A. Given that the child has a gene is B. If I go to C, what is the probability that the child has a gene? That's A, has a gene, that's A. Given this is the vertical line, the child has a high IQ, that's B. So there's always two events happening when you do conditional probability. Any questions, guys, about conditional probability? We'll practice a little bit more. We'll do another example. But if I give you conditional probability questions on the test, it will be in the context of a table. So it's very, very important, guys, to understand how to use the table. It will be just a table like this, but with different, headings and different information. But to answer the questions, you just follow exactly what I did right here. All right. When do we say that two events are independent? we're going to learn about definition of independent events and one possible question of the test. I'll give you two events, two situations, and I'll ask you, are they dependent or independent? So let's give you the definition so you'll make sense of it, guys. We say that two events are independent if the occurrence of one event does not affect the probability of the occurrence of the second one. So if they have nothing to do with each other. If one event happens, the second event, if it happens, it has nothing to do, just with the first event. And let's give you an example so you'll make more sense of it. Decide whether the events are independent or dependent. So example 1. A standard deck of cards, guys, has 52 cards. You select a king from a standard deck and you don't replace it. What is the probability of selecting a king, guys, from a standard deck of cards? If I just give you a standard deck of cards right now and I ask you to select a king, what's your chance of getting a king? Does anyone?
4 out of 52.
4 out of 52, because there are 52 cards and there are 4 kings in your favor. So it's 4 out of 52. What is the probability of selecting a queen? There are 4 queens in the standard deck of cards, guys. So your chance of selecting a queen is the same, which is what? 4 out 52. Now look what he says here. You have a standard deck of cards, 52 cards. You select one card, and you want to check if it is a king. Your chance of getting a king is 4 out of 52. You don't replace the card. You know what not replacing it means? You didn't put the card back. And now select a queen. Do you think the events are dependent or independent? So the first event is to select a king. The second one is to select a queen, but you did not put the first card back.
So wouldn't that be dependent?
They are dependent because the queen, if they are independent, the probability should be 4 out of 52. But now the probability, guys, is not 4 out of 52. We were working with less cards, so we're working with 51 cards. And that violates the definition with the probability of the queen, which should be 452. So as a result of my action, not replacing the card, the events became related with each other, which is 4 out. Here it's going to become 4 out of 51, guys. So that means the events dependent. Okay, what about number 2, guys? You toss a coin, you get a head, and you roll a die. In one hand, you toss a coin, and in another hand, you roll a die. Do you think those two events have anything to do with each other?
No.
No, they're independent. The probability of getting a head is 1 out of 2, and the probability of obtaining a 6 is 1 out of 6, and that doesn't change no matter, just what the type of coin I use. The probability of getting a 6 on a die is always 1 out of 6. That does not change, independent. All right. I'm going to give you some more examples from the book. Let's review some more examples on dependent and independent. All right. So you guys can confirm you can see the screen, correct?
Yeah.
Okay. Classify the events as dependent or independent. So if they're not independent, that means they are dependent. What do you think about number 10? We did number 9, guys. That wasn't my handout. A father having hazel eyes and a daughter having hazel eyes.
Dependent.
Dependent because, yeah, the daughter could take after, just her father. Yeah, that's in the genes. What about 11? Returning a rented movie after the due date and receiving a late fee.
Dependent.
Dependent, because as a result of not returning the movie before the due date, they assess a late fee. 12. Not putting money in a parking meter and getting a parking ticket.
Dependent.
Dependent. If you don't put money in the parking meter and you get caught, they're gonna issue you a ticket. 13. Rolling a 6-sided die and then rolling a die a second time so that the sum of the two rolls is 5.
Dependent.
Do you guys agree it is dependent, because what we get on the first die, it determines what we need to get on the second one. For example, if the first roll gives me a 3, I need a 2 to get a 5, so they're related with each other. If I get a 4 on the first die, I need a 1 in order to get a 5. But if I get a 6 on the first roll, guys, I will never get a 5 because this is way above 6. So they're depending on each other. Number 14. A ball is selected from a bin of balls numbered from 1 through 52. We select the ball, we look at it, and then we put it back. It's replaced. That means we put it back. And then second numbered ball is selected from the bin. What do you guys think?
Independent.
Independent. Because the first time you're selecting out of 52 and the second time you're selecting out of 52 again. It's not like the standard deck of cards where I kept, the card, just outside and I didn't put it back. Here you put it back. Replace means you put it back. So that that means the two events are independent. Okay. Here's one of my favorite here. Event A, driving a BMW, and event B, getting into a car accident. What do you think, guys, the two events? Dependent or independent? I know some students sometimes argue this, but
Independent.
what about if I tell you I think they are dependent? People, why would people buy a BMW? Sports car. What do you think one of the reasons, guys, someone would invest in a BMW?
Safety.
Rides fast.
Well, safety, yeah, but people want it because they want to drive fast. Yeah, these are known as sports car. And if it is a sports car and it drive fast, probably you'll be inclined, just to drive fast. And if you drive fast, there is a likelihood that you get involved in a car accident. So I always argue that the two events are dependent. If someone want to argue otherwise, I don't think you'd see someone, just invest in a BMW and driving it, just below the speed limit. I never seen that before. So just to give you some definitions, guys, about dependent and independent events. Good? Okay, I'm going to go to the next. Paper, which is number 5. And let me just take you back to my other screen. There we go. Okay. If two events are independent, guys, that means the probability of A and B, event A and event B is probability of A times probability of B. And I'm going to give you an example right away, right here. This is a very good example to explain this. We toss a dime and a die is rolled. Find the probability of getting ahead and then rolling a 6. Okay, so this is the first event. That's the second one. Okay, and this is the die. Okay, let's list all the outcomes, guys. We did that on Monday. So you roll a die and you toss a coin. What are the possible outcomes? And I think I remember last time, guys, you gave me H1, H2, H with 3, head with 3, head with 4, head with 5, head with 6. And then tail with 1, tail with 2, tail with 3, tail with 4, tail with 5, tail with 6. And we counted 12 outcomes if you go back and review what we did last time. Okay, he wants a probability of getting a head and a 6. How many outcomes are there, guys, that have a head? So we have 12 of them in the denominator. And how many of those outcomes will give me a head and a 6? You guys agree there's only one outcome, so it's 1 out of 12. So this is the answer to the question. Now I'm going to show you how to answer this question without even going through this and counting the outcomes. Do you guys agree with me that if we toss a coin and roll a die, the two events are independent? They have nothing to do with each other. They're two different actions. They're not related, so they are independent. So here's what I'm going to ask you to do for me. What is the probability of getting ahead, guys? Who can tell me what's the probability of getting ahead when you toss a coin?
1 out of 2.
Exactly. Okay, now we roll a die. What's the probability of getting a 6?
1 out of 6.
Yep. I'm going to put a multiplication sign in between. I like you guys to multiply 1 over 2 times 1 over 6. What do you get? You multiply fractions by multiplying the numerators and the denominators straight across. What's the answer, guys? What's 1
1
over?
over 12.
There you go. It's already there. So if two events, guys, are independent, and I ask you what's the probability of the two events happening together, A and, when I say the word and, guys, means the two events, you notice, are happening together at the same time, you just multiply the probabilities. It will be 1 over 2 times 1 over 6, which is about 80%, yes, which is 1 over. So here's a possible question, guys, in your homework. Very easy question. He gives you probability of A 0.321. He gives you probability of B to be 0.417. And he tells you A and B are independent. And then he asks you to find the probability of A and B. A and B, guys, means the two events happening at the same time together. So the probability of A and B, if they are independent, you just take the probability of A and multiply it by the probability of B. So that will be 0.321 times 0.417, and then you just get the answer. And I want to share with you an example I used to give all the time to students when we used to do the tests. On campus, so it's 0.134. That's the answer. Okay, here's another example. I tell students, I set up 2 alarms every day to wake me up, on time. But just an alarm by itself, and then my phone. Let's say that the probability that the first alarm will malfunction is 0.025. That means it will not go off, when it's supposed to. It won't work. The chance is only 0.025. And let's say the probability that the alarm on my phone will not work is 0. It has to be low. Otherwise, we won't use those devices. If the probability that they malfunction is high, nobody would use it. So this is the probability the second device will malfunction. I set up the two alarms, guys. What is the probability that both of them will malfunction in one day? First of all, guys, we agree that the two devices are independent of each other. Because I told you I'm using a standalone alarm and I'm using my phone. So two different devices. They have nothing to do with each other. So the probability that the first one will malfunction is 0.025, and the probability that the second one will malfunction is 0.013. If I ask you the question, what's the probability that both of them, it will be really extremely bad luck. Both of them will not go off, and I won't wake up, on time. Let's see what the chance is. To figure out the chance, guys, you just multiply the two probabilities. So if you multiply, what do you get? It's going to be very low, guys. So it's very unlikely to happen. 0.025 times, what did I put there? 0.013. And this is the answer. If you multiply those two numbers, guys, you get this, which is a very, very low probability that this will happen. So if you don't trust, just one device to wake you up on time, use two of them, and the chance that one of them is going to work, it's going to be very good, because the chance that both of them will not work is 0.0000325. Okay? Let's go to do some more examples on independent events. So I'm going to do part A here for this example. And please, guys, participate with me. I only hear a couple or three students, just participating, but I want the rest of you. And actually, I'm changing the way we do things. You're going to be going to breakout sessions and to work, just with each other eventually in this class. The probability that each knee surgery is successful is 0.85. So a surgeon performs knee surgery, and the chance of success, guys, the probability is 0.85. The doctor performs a surgery on 3 patients. What's the probability that the 3 knee surgeries are successful? How would you figure this out? Ask yourself this question, guys. Do you agree that the 3 patients are independent of each other? They're 3 different patients, 3 different knee surgeries. They're not related. They have nothing to do with each other. And the probability that each one of them will have a successful surgery is 0.85. So what do you think, guys? What's the probability that the doctor will perform the 3 surgeries and the 3 of them are successful? Any input? Yes? We want the first surgery to be successful, the second surgery to be successful, and the third surgery to be successful. So probability of first surgery successful times it's a conditional, it's independent events. Probability of second surgery successful times probability of third surgery successful as well, guys. So the answer will be 0.85 times 0.8. We don't add them. If you add them, you go above 1, which is impossible in probability. So 0.85 times 0.85 times 0.85. And let's do this. I got 0.614. Any questions, guys, here? So because the three patients are independent of each other, you just multiply the probabilities. So 0.85 for each one. If you were tempted to add the probabilities, guys, add in, but look, see, you're going to get something that's impossible in probability. Let's say a student's by mistake add them. 0.85 plus 0.85 plus 0.85. You get 2.55. You know a probability cannot exceed 1. It's impossible for a probability to exceed 1. So if you're doing any work in chapter 3, guys, and you end up with a number bigger than 1, you better not put it as an answer. I would rather that you don't do nothing and don't put an answer that goes above 1. There is no such a thing called above 100%. Your capacity is 100%. The probability does not exceed 100%, which is 1. And probability doesn't go below 0. It's between 0 and 1, guys. It could be 0. If the probability is 0, that means the event will not happen for sure. And then if the probability is 1, that means the event will for sure happen. And if a probability between 0 and 1, then there are chances of the event to happen, but not 100%. Part B, what's the probability that none of the three surgeries is successful? So that means what's the probability that the first one was not successful, the second one was not successful, and the third one was not successful? Who can help me with that?
Would we just subtract 1 minus the 0.614?
No, it doesn't work this way, but you're close with the plan. Let me tell you why you cannot do this. Because it's not either 3 of them are successful and none of them are successful. What about if 2 of them are successful and 1 is not successful? We didn't account for that. So I'm going to show you a different, easier way. Would you guys agree with me that the probability of 3 surgeries not successful means the first one is not successful, and the second one is not successful, and the third one is not successful? And guys, means multiplication. So what is the probability that the first surgery is not successful, guys? If the chance of success is 85%, what's the chance of failure?
0.15.
0.15, guys. If you know your chance of success, you know your chance of failure. Exactly, 15%, yeah? You need to know that. If I tell you the chance that you're going to get an A in my class is 90%, then the chance you're not going to get an A in my class is 10%. You should know that right away, because the yes and the no add up to 100% always. So it's going to be 0.15% for the first patient, and 0.15 for the second patient, and 0.15 for the third patient, and let's see what will be the answer. It has to be very low, otherwise this doctor, this surgeon will be in serious trouble. I mean, imagine that a surgeon is performing 3 surgeries and his chance of success, he tells his patient that the chance of success is 85%, and then he performed 3 surgeries, and then all of them will be not successful. That should not happen. And let me show you the answer. What is it going to be? 0.15 times 0.15 times 0.15. Okay, here's the answer. Can you guys help me change this one to a percent? What would that be as a percent? To change a decimal to percent, you move it 2 digits to the right.
Do we multiply it by 100?
Yep. The chance that a surgeon whose usually success rate is 85%, the chance that that surgeon will do 3 surgeries and none of them will be successful, it's not zero, guys, but look how low it is. It's not even 1%. So it's very unlikely to happen. Very unlikely to happen. So it's 0.33%, a third of a percent. It's not ruled out, it's not zero, but it's a 0.3375%. Okay? Any questions, guys? I did make some change here. I just erased this part and put none of those. So just take a note of that if you're using your guided notebook. But I will share this with you today after we're done with the lesson. So for independent events, guys, all I want you to do or to know, if I tell you A and B are independent, that's the rule I want you to know. And if I ask you to find the probability of A and B, then you tell me it is a probability of A times probability of B. This formula is only valid if the events are independent. If the events, guys, are not independent, then this formula is not valid. You cannot use it. It's only valid for independent events. Probability of A. And the end, for your information, guys, means two things are happening at the same time. So A and B. A stands for an event and B stands for another event. And we use capital letters, guys, to label events. So event A, event B. Experiment A, experiment B. All right. Now we're going to learn about mutually exclusive events. We say that two events are mutually exclusive if they cannot happen at the same time. So I'm going to write it down again. Two events. And then I'll show you some examples from the book. Are called mutually exclusive if they cannot happen at the same time. All right. Let me do a sketch and tell me, guys, if you think the events are mutually exclusive, so or not. This is event A, and this is event B. What do you think? Mutually exclusive or not mutually exclusive? Mutually exclusive means cannot happen at the same time, cannot occur at the same time.
It's not mutually.
Do they have anything in common? This is event A and this is event B, and they're separated. These two events are mutually exclusive because there is nothing in common in between them. They cannot happen at the same time. They don't have any intersection. So mutually exclusive. I know it's confusing to students. Sometimes the students think of mutually exclusive as they can happen at the same time. No, mutually exclusive means cannot, with the word not, N-O-T, happen at the same time. That changes. So this is mutually exclusive, guys. I'm going to give you lots more example to understand this. Let's take this now. Now, if I ask you, are the events mutually exclusive, you tell me no, because you see there is an area where A and B overlap. They can happen at the same time. So a part of A and part of B mixed together to happen at the same time, then this event are not mutually exclusive. Okay, let's give you some more examples, guys. Okay. More examples on mutually exclusive events. Two events, A and B, are mutually exclusive when A and B cannot occur at the same time. That is, A and B have no outcomes in common. That's a good, he says that as well. And look, guys, mutually exclusive, not mutually exclusive. That's the example that I started with. Okay. What do you think of number one, guys? Event A, you roll a 3 on a die, and event B, you roll a 4 on a die. Can you get a 3 and a 4 at the same time, guys, when you roll a die?
It's mutually.
Mutually exclusive? They are, because you cannot get a 3 and a 4. It's going to be face up. If your die is not loaded, it's a fair die. If it is a 3, it can't be 4. And if it is a 4, it can't be 3. So they are mutually exclusive. Okay, what about 2? Randomly selecting a male student and randomly selecting a nursing major. Ask yourself, is it possible to select a male student who is a nursing major? If your answer is yes, that means the events are not mutually exclusive. If they cannot happen at the same time, if it is impossible to have a male student and a nursing major at the same time, then they are mutually exclusive. What do you think of number 2, guys? Are there any male students who happen to be nursing major? Yes or no?
Yes.
Well, if it is a yes, then they're not mutually exclusive. So not mutually exclusive. As long as there is an overlap, guys. Okay, number 3. Randomly selecting a blood donor with type O, randomly selecting a female blood donor. Is it possible to select a female blood donor who has a type O?
Yes.
Then the events, if your answer is yes, that means the events are not mutually exclusive. It has to be a no. In number 1, you told me it's not possible to get a 3 and a 4 on the same face of a die. Then that's why they are mutually exclusive, and that's a 3. Because the donor can be a female with type O blood, the events are not mutually exclusive. Okay, let's do some more. Now you try it. Okay, for students who don't know about standard deck of cards, there are 4 jacks in a standard deck of cards, and there are 4 queens and 4 kings. So 12 pictures, guys, in a standard deck of cards. And they are called faces. So the jack, the queen, the king are called faces. So you randomly select a jack from a standard deck of 52 playing cards. That's event A. And randomly selecting a face from a standard deck of 52 playing cards. The question is it possible to select a face that turns out to be a jack, guys? Yes or no?
Yes.
Then if your answer is yes, the events are not mutually exclusive. Not mutually exclusive. What about number 2, guys? Can you select a vehicle that turns out to be Ford and Toyota at the same time? To my best of my knowledge, Ford did not buy Toyota yet, or vice versa. So what do you
No.
think of the events? So the events are mutually exclusive. You cannot have a vehicle that is Ford and that vehicle at the same time is a Toyota. That can't happen. Okay? This is what I would like you know just to know about mutually exclusive events, and I want to give you some more examples just to have a good feel about it, guys. So let's see. I'm gonna go to the exercises. There we go. Number 9. Determine if the events are mutually exclusive or not. Look, guys, here, not mutually exclusive. They have intersection. Here, mutually exclusive, they don't have intersections. So I think you should know that by now, but let's do some more. You should be able to answer now. You know, when you do your homework online, you might see some of those questions again, just pop in, but with different probably letters or wording. So number 9, and just for your information here, when you see this, if you click on it, guys, let me just show you. What you would see here. It will just work it out for you and explain, you know, just the process. So you can do practice exercise while even exploring the textbook. Randomly selecting a male psychology major and randomly selecting a psychology major who is 20 years old. Ask yourself the question, is it possible to select a male psychology major who happened to be 20 years old?
Yes.
Yes, okay, I have a yes here. Let me just annotate. If it is a yes, that means not mutually exclusive. That's no. Not mutually exclusive. 10. Randomly selecting the students with a birthday in April, randomly selecting the students with a birthday in May. Is it possible to select the students who happen to have a birthday in April and May at the same time?
No.
No, can't. So these are events 10 are mutually exclusive. Mutually exclusive events. 11. Randomly selecting a voter who is a registered Republican and randomly selecting a voter who is a registered Democrat. By law in the United States, it can't happen. You cannot belong to two parties at the same time. That's unlawful. It's not allowed by law. So they are mutually exclusive. Can't be a Republican and Democrat at the same time. You will go to jail if they find out. Number 12. Randomly selecting a member of the U.S. Congress and randomly selecting a male U.S. Senator. Can a member of the U.S. Congress be a male?
Yes.
Yes, so that means the events are not mutually exclusive. So if they overlap, guys, in final words, if the two events overlap, you think that they could happen at the same time, then it's not mutually exclusive. If they don't overlap, just like this right here, then they are mutually exclusive. So any questions about the definition of mutually exclusive events? Now we're going to go to the next concept, so I'm going to stop. Okay, guys. Addition rule in probability. We have this and a few more things, and we should be able to wrap up the chapter and do some more practice. Let me tell you what the addition rule is. Okay, the sample space, as I told you at the very beginning when I first introduced the chapter, is the set of all possible outcomes. For example, if I roll a die, guys, my sample space is all the possible outcomes. So it is 1 or 2 or 3 or 4 or 5 or 6. That's what the sample space means. If I roll 2 dice, my sample space is 36 possibilities because it's 1, 1, 1, 2, 1, 3, 1, 4. I listed them for you the last time. So the sample space is the collection of all outcomes. Let's suppose my sample space, guys, has those numbers in it. I'm just making this up. So my sample space has 11, 1, 15, 3, 2, 10, 9, 4, 7, 25, 20, 19, 8, 16. These are all the possible outcomes. Now I'm gonna circle an event. And I'm gonna call it event A. So my event A has a 2, a 4, a 9, a 16, and a 10 in it. And now I'm gonna circle an event B, guys. And B has 16, 4, 7, 20, 25, 8, 19. I'm going to start asking you some questions, and I would like you to help me with this. So we're going to review what we did, and then we'll come to the addition rule. I'll explain the addition rule to you. You select a number. You close your eyes, guys, and select a number at random. So I'm closing my eyes, and I'm picking one number. What's the probability of getting a number in A? So who can tell me what is the likelihood that we're going to select a number and that turns out to be an A? But remember, you're picking at random, you're not looking.
1 out of 14.
Okay, you have 14 total. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So I agree with this. I agree with the 14, but I don't agree with the numerator. If you select any number in A, you will be successful. And you limited yourself to only one number. How many values are there in A?
5.
5. So your chance is 5. Why do you want to limit your choices? My choice of winning in A, let's say this is a game you're playing, guys, and you would win if you get a number in A. Your chance of winning is 5 over 14. It is a good chance. It's not bad because it's not very close to 0, so it's not a bad chance, but it's not a very great chance that you say that I'm going to win. So it's 5 over 14. Okay, here's my second question to you guys now. You close your eyes and you pick a number. What's the likelihood that this number is going to be in B now?
7 out of 14.
Okay, you got 14 total. You're picking from the basket that has 14. The likelihood that you would win if you get a 4. You would win if you get a 16. You would win if you get a 7. You would win if you get an 8. You would win if you get a 5. You would win if you get a 20. You would win if you get a 19. I agree with you. It's 7 out of 14. Is everybody okay so far, guys? That's very, very important because I'm going to just come up with a definition for the addition rule from this example. I usually do it with an example. Students get it, and I don't need to go back in theory and explain the formula. I just construct the formula. Okay, now, here's the question, guys. Next question. What is the probability if I put those numbers in a basket and pick a number? What's the probability that this number will turn out to be in A and B at the same time? A and B, which is called the probability of A and B, guys.
2 out of 14.
Okay, let's see if the rest of you agree with this. Yes, it is 2 out of 14. 14 is, we're picking from the basket, guys. And the basket has 14 items. You cannot change that. It is 14 in the denominator. Now, look, the numerator is you ask yourself, what would work in my favor? That's the question that you want to ask yourself when you do your homework. What would work in the favor of the question? How many values? I don't care whether this is a 4 or 8 or 9. I just care how many are there. You count them. 1, 2. 2 values out of 14. So you have 2 chances out of 14 chances to win. 2 out of 14. Okay, here's the next question, guys. And that's the addition rule now. You see what I put here, or B. If I ask you guys, okay, we have a meeting, and I tell you, if you bring chapter 1 notes or chapter 2 notes, that would be fine. I can look at either one and give you a grade, just on note taking, for example. What I'm trying to tell you guys, if you bring chapter 1 notes, that's good. If you bring chapter 2 notes, that's also good. It's either this or that. So you will be successful if you show me chapter 1 notes, and you will be successful if you show me chapter 2 notes. You don't have to show me both. I said this or that. So now I'm asking you to find the probability of A or B. The probability of A or B means you will be successful whether you pick from A or pick from B. So guys, you have the diagram, and I'd like you to tell me what is the probability of selecting a number that turns out to be in A or B. And the denominator, there is no argument, it should be 14. So can you tell me what's the numerator here? If you pick from A, you're good. If you pick from B, you're good.
10.
Okay, let's see how many. Let's count them. 1, 2, 3, 4, 5. I'm not going to count these two again. When I take attendance, guys, I don't count you twice. I can't do that. Even if you change your seats and move somewhere else in the room, I cannot go back and count you, not just again. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Excellent. Okay, guys, here's my final conclusion. Actually, guys, I didn't need even to do any work to find the probability of A or B. I would like you to look at what we did here and see if you can use those 3 answers to construct the answer that we got, which is 10 out of 14. What would you have done with those 3 answers to get the 10 out of 14, guys? Look at them. Find a relationship between those 3 in order to get the 10. The 14 is the common denominator, so that's a given. We're going to get it. But what would you do with those 3 answers in order to get 10?
Add A and B and then subtract.
And that's the addition rule, guys. That's the addition rule. So the addition rule says, and now you're asking me, why do I need to do what you're saying if I can do it this? Sometimes, guys, it doesn't give you, it just give you those 3 values and tell you find, probability of A or B. So here's the rule, guys. Probability of A or B, which is called the addition rule. It's a probability of A plus probability of B minus probability of A and B. And let me tell you why we don't just add in. The minus is to add what's repeated. You cannot, count something twice. So if anything has been counted twice, we remove it using negative probability of A and B. So look, guys, 5 over 14 plus 7 over 14 minus 2 over 14, it's going to give me 10 over 14. And bingo, it's exactly the same answer that we got right there. And this is what we call the addition rule. Okay? I'm not requiring you to, I will allow you not just on the test to use your notes, so you don't have to memorize the formula, but this is a formula that try to remember. It's a good one for the addition rule. Okay. So there's a formula right here, guys. Probability of A or B is probability of A plus probability of B minus probability of A and B. Okay? That's what I explained to you. Now, if A and B are mutually exclusive, what is the probability of A and B? If two events can't happen at the same time, they have nothing in common. What is the probability of A and B, guys? If I tell you you have two events, and that could come up, just on the test. I tell you A and B are mutually exclusive. What's the probability of A and B?
A plus B.
A, not A or B. I say A and B. Remember, mutually exclusive means they have nothing in common. And A and B means what do they have in common? So what would be probability of A and B?
You don't just add them?
No, you should know what the answer is. What's the probability that today is Tuesday and Wednesday at the same time?
A or B?
It will be 0. When two events are mutually exclusive, guys, the probability that the two events happen, they have nothing in common. Because when we do A and B, look here, guys. When I did A and B, I looked for the intersection. But when they don't have intersection, it will be like this. This is A, watch. This is A, and this is B. And I'm asking you guys to find the probability of A and B where they have nothing in common, so it is 0. So here, this is what the formula says. If the events A and B are mutually exclusive, then probability of A or B will be probability of A plus probability of B. Well, there should be a minus probability of A and B, but because they are mutually exclusive, this intersection is 0, so you get this formula. So this formula, guys, probability of A or B is probability of A plus probability of B is valid only if the events are mutually exclusive, and it says here. Okay, let's do, you roll a die. What's the probability of rolling a number less than 3 or rolling an odd number? Okay, I'm going to just do a sketch for this, guys, and then I'm going to show you it's very easy. So if you roll a die, you get 6 choices. 1, 2, 3, 4, 5. And we put the 1 here. 6. Okay. What is the probability of rolling a number less than 3 or rolling an odd number? So rolling a number less than 3, I'm going to call it event A. And an odd number, I'm going to call it event B. And he wants the probability of A or B. According to the rule, guys, it's a probability of A plus probability of B minus probability of A and B. Okay, you're going to help me here. What do you think the denominator is going to be for all 3 parts? Okay, I got something in the chat. 6, yes. Very good. Okay, what's the probability of rolling a number less than 3? I got this and that. So the answer will be what, guys? How many?
2.
2, not 3. Less than 3 doesn't include 3, guys. Remember, less than 3 doesn't include 3. So it's 1 and 2. So 2 out of 6. Plus. What is the probability of rolling an odd number?
3 out of 6.
Yep. Do you guys agree? Look,
Yes.
these are the odd numbers. Watch. Trying my very best, guys, to make it as easy as possible to comprehend. Minus. Now we have to rule out the repetition. You cannot repeat in probability of event. What is the probability of getting a number less than 3 and at the same time being odd? Where do the 2 overlap, guys?
1.
1 out of 6, exactly. And that would be your answer. 2 plus 3, 5, minus 1 is 4 over 6. And that's the answer. All right. Let's look at this example here. A frequency distribution shows the volume of sales in dollars and the number of months a sales representative reach each sales level during the past 3 years. If this sales pattern continues, what's the probability that the sales representatives will sell between $75,000 and $124,999? Okay. Who knows how to do this? What is the probability? So these are 36 months, guys, together, 3 years. Does it say? Yeah, 3 years. So if you add the month, they're going to be 36 months. So we know the total of all frequencies is 36 months. All right. You want your sales to be between 75,000 and 124,999. But if you look at the categories, guys, you have 75,000 to 99,999. So this is where your sales could be. If your sales are here, you're good because that's from 75,000 and up. Or your sales could be 100,000 to 124,999. So what do you think the probability that your sales could be from 75,000 to 124,099? So
16 out of 36.
So it will be 7 over 36 if it is from 75,000. Or, and what's or? What's the symbol for or? It's addition. 9 over 36. And if you ask me where I got them, guys, your sales could be from 75,000 to 99,000, or they could be from 100. And see, when I say the word or, it's a plus. Between 100,000 and 124,999. Now, probably, guys, you'll ask me, where's the minus? There is no minus here because the events are mutually exclusive. They don't overlap. Look, guys, you go to 99,999 and then you jump to 100,000. There is no intersection in between the two. And that's why you just add the two probabilities. So that will be 16 over 36. Okay, guys, you can take your